If you just have questions on where we're getting stuff, you just let us know. Yeah, should be chill. All right, it's 5:02. I'm going to start. All right, cool. Well, you know what the deal is. Where it's just you for now, but hopefully we get some other people coming in. I do not know if we will, but I mean, it's
There's one if you want to. I don't know what the exam is about.
all right, fair enough. All right, so I guess we'll just start. So welcome to Let's Diff Mid-Semester Review. So we're basically just going to be going over chapter 2 for like the first half of it, the second order differential equations, just because that'll be a lot easier. The camera's way back there. You're going to be getting some whatever. All right, cool. Second order differential equations. So it's the same procedure as the first orders, but now we have to take a second derivative of the y particular. So it makes it a little bit more complicated, but it's a lot of the same concepts, a lot of the same, functionalities or whatever. But, we have some basic ones here that you can look at. So using undetermined coefficients is a really great way to do second order differential equations. In my opinion, it's my favorite way to do it because it just makes the most sense to me. So like if you look at the top left here, at the y double prime plus 9y equals e to the 2t one, you know that your solution is going to have the form of some constant, call that a of e to the 2t, and then you can go through and derive it, and we'll do some examples with that as well that you'll see. But yeah, so because when you take the derivative of a e to the 2t, right, that's going to be 2a, if you take the prime of that, that's going to be 2a e to the 2t. And so this term, you have to make sure your left side has that term so that your right side can have it. Like since it's on the right side, it has to be on the left. Basically, yeah, that's exactly it. And you will, like I said, we'll see a bunch of examples through it. We'll go through a couple and you'll see how it all works. But it'll be really nice. So yeah, basically that's just what undetermined coefficients is. It's seeing what your right side is and then taking that and going to your left side. That's basically how that works. So we'll go through. Here's a couple of common particular solutions that you can look at. So right here we have our a e to the st. That's the one I just showed you. It's a very common one. If you just have like some, if I like made up some equation, some like, I don't know, some like 3e to the a million t or something. I don't know. That means that your left side has to have that same exponent. That's basically all that's saying. And then you like have the other ones. You have a couple other ones that are like, you have your at squared plus bt plus c. That's another one you can do if you have like a t squared on your right-hand side of your equation. That's one that you can do. You have the sinusoidal one. So if your second order differential equation is equal to like some sine or cosine, that's what your particular solution is going to look like. And you can use that as well. And then for products, it's the same deal. And like I said, we'll go through some examples and you'll see how it all works. So first example is going to be this one. So tackling this one we're actually going to do second because I thought it was pretty complicated and I'd like to do the other one first, and then we'll come back and do this one. So example number 2. This one is about as simple as you can get when it comes to the trigonomic undetermined coefficient part of it. So we have our equation. We have y double prime minus 6y prime plus 9y equals 25 sine of 6t. So
Make it so there's actually one.
hey, that sounds good. Sounds good. We just can follow it so far. So, all right, cool. So in our complete solution, right? That's what we're trying to solve for. We're trying to solve for what is our complete solution. And since there's only one of you in here, I'm going to ask you, what is our complete solution going to be comprised of? Particular and the null, right? Perfect. So we have the null and we have the particular. So the first step we're going to do for this, we're going to solve for our null solution. That's going to be the first step of this, right? So solving for our null, we're going to have y double prime minus 6y prime plus 9y equals 0. So this is going to help us solve for our null solution. So the first step with this is what? So it's going to be solving for our roots, right? That's going to be the first step of this, right? So exactly, right? So we're going to have r squared minus 6r plus 9 equals 0. We do some basic, factoring, and we're going to have r minus 3, r minus 3. Now, we have a repeated root, so we're going to have some special case with that. So r is equal to 3, 3. So since our root is repeated, our y null solution, not only will it have the form of some constant e to the 3t, it's actually going to have another part to it. And it's going to be plus some other constant t e to the 3t. See how that works? So that is what our y null is going to look like. So now we have to take the derivative of that and the double derivative of that and figure out, all right, no, never mind. I lied. We don't have to do that because we don't know what we're plugging in yet. So yeah, that's what our y null is going to look like. It's going to have some form like that. So now we can start solving for our particular, right? So now we're going to use this equation. So with our particular solution, what do you think our solution is going to look like? It's going to be some a sine of 6t, but you have to remember the cosine as well. Because when you take the derivatives of sines and cosines, right, the derivative of cosine is negative sine, you have to take both into account because they both could matter. And if you just made it a sine of 6t, you're going to have a cosine. And when you take the derivative of that again, you're going to have a sine. That sine is not going to be able to cancel. That cosine is not going to be able to cancel out anywhere. Do you see what I mean when I say that? So we have to have this form for our particular solution. So that is what our regular y is going to be. But in order to solve for our coefficients, we're going to have to take the derivative and the double derivative of that. So what would our derivative of that be? Just from left to right. Correct. Yep. Perfect. So that would be our y prime of our particular solution. What would our y double prime of our particular solution be? Cosine of 60, right? Yeah. Yep. So boom, there's our derivative and there's our double derivative. Perfect. So now we can plug it into our original equation over here and we can solve for our coefficients, which we will be able to do. So we're going to plug that in and it's going to be a whole big long mess. So here we go. I wonder if we have, yes, we do. Perfect. All right, so I'm going to go ahead and plug it in. I have the notes from the last one, so it'll be just fine. So our solution is going to look like this. It's going to be negative 36 a cosine of 6t. Is that right? Yeah, that's right. Yeah, so it's going to be negative 36 a cosine of 6t. What did I do? I don't remember what I did last time. All right, we'll change that because I had it written different over there. So we'll change it, make that b. All right, so negative 36b cosine of 6t minus 36a sine of 6t. Okay, cool. And then we're going to have minus 6. So this was our y double prime right there. So now we have our y prime. That's going to be minus 6. Look back over here. 6a cosine of 6t minus 6b sine of 6t. Perfect. And then we're going to have our plus 9 of our y. And that is going to be, look back here, a sine of 6t plus b cosine of 6t. Okay, you see all that? And that's going to be equal to, I'm running out of room here. All that is going to be equal to our original solution, which was 25 sine of 6t. Do you see where we're getting all that from? Right, all we did was just derive our undetermined coefficients of our particular solution and plug it in. So now we just have our a's and b's, and we can solve for them by combining like terms. So that's how we're going to do this. So I'm going to simplify this. Do you want me to go through all the simplification, or do you want me to just write it all simplified? All right, cool. then I will do that. So I wrote it wrong on here. I have to flip my A's and B's. So when we simplify it all, it's going to come down to this. It's going to be a negative 36b minus 36a plus 9b equals 0. And then we're going to have a negative 36b plus 36a. Oh, wait, hold on. Change those. Yeah. Negative 36a plus 36b plus 9a equals 25. So that's what's going to simplify down to. We're going to get that system of equations. Two equations, two unknowns. We can solve for it. Do you want me to solve it, or do you want me to just give you the solution? What do you think? Just fine giving the solution? All right, cool. So when we do that, we are going to have that our a is equal to a negative 1/3, and we're going to have that our b is equal to 4/9. That's our solution. So then when we find for our complete solution, right? So our final answer is going to be our complete solution. And that is going to be our y null plus our y particular, which our y null solution, if we go back a couple slides, is going to be equal to ce to the 3t plus dt e to the 3t, and then plus our particular solution, which we have our a and our b now. So now we can look at our particular, and it's going to be minus 1/3 sine of 6t plus 4/9 cosine of 6t. And double check that that corresponds. It does. And there will be our final solution for our complete. Now, if we had initial conditions, that's where we would plug it in and solve for our constants. So if we had like, y naught is equal to, let's say 3, then we could plug in our t equals 0 into this equation and solve for what will be our c, because our d term will go away. And then we could take like a prime and solve for that way as well. So that would be our complete solution for that problem. Any questions on that one? Or you see where we got everything? Sounds good? Cool. Cool. So I guess I'll ask you, do you want to go through this problem? Or would you rather we just skip on and go to the next thing? Because it's just another undetermined coefficient problem. It is a lot more complicated. I won't lie to you, but it doesn't involve Euler's formula. It does.
Do you want to have a go at it?
And I will tell you, so if you want to, there's going to be a spring application later that we can do as well. And that one also involves Euler's formula. So it's up to you, whatever you want. You're fine not doing it? All right, cool. Then I will just skip it, and I'll give this over to Michael. And yeah, it just shows that we did all that.
I forgot to have a blank slide for this example.
Oh, well, it's fine.
Which is fine because I can just open the OneNote.
Yep, it'll be fine.
All right.
All right, here, take this.
Oh, snap. I
That's
forgot
right.
about that.
Yes. Good, sir. And just click this onto like your collar or whatever. Here in your mouth. The gold. Oh, yeah.
Like right there.
Yeah,
Okay.
that works.
All right. Do you have one of these sheets for reference? Yeah, sure.
Add it up here. I got you.
Just might be handy for some of our examples.
He spent some time making these sheets. They are pretty useful. Heaven will not give you these. And we wouldn't say necessarily for Heaven's class, we'll tell you not necessarily to rely on them completely, but they are really nice to for referencing.
Yes. So the section that I'll be covering is concerning the Laplace transform, which is a really effective tool in solving ordinary differential equations. It's almost like it's like a way to get it done really quick if we need to, compared to some of the other methods that we have. So here on the left, we can see what the definition of the Laplace transform is. And on the right here is an example of of an ODE that we're going to solve with the Laplace transform. So let's move over to OneNote and write this example down. So let's say we have y double prime plus 3y prime plus 2x equals 0. So that's our ODE. And then let's look at our initial conditions. We're going to have y at 0 is equal to 0. And then also at y prime at 0, that's going to be equal to 1. So our first step when we're going to be using the Laplace transform is we're just going to take the Laplace transform of this whole thing right here. So when we do that, let's see, we're going to be, oh, snap, that's a little large. I think it's this one. Yes. What? Yeah, it just disappeared on me right there. It's actually the first time I'm using this thing, so is this right? Why is this so large? Oh, I think I need to be in pencil mode. Here we go. I think this is it. Yep. Okay, all right. So the Laplace transform of a sum is the sum of the Laplace transforms. Does that make sense? So if I just take the Laplace transform of this whole thing, oh, snap, that is wrong. That should be a y. Yep, you are correct. It's just each one plugged into the Laplace transform. So if we use our handy dandy sheet or we just remember it, we'll know for our, yeah, tables. For y double prime, we're going to have s squared, capital Y, minus s y at 0 minus y prime at 0. That's going to be our first right here. And then the next one is going to be 3 times, which is going to be s capital Y minus y at 0. And then for our last, we're just going to have 2y. Does that make sense how we got there? All right, cool. So when we go and plug in, yes. Yep. So when I just do this guy, I just denote it as capital Y. So that way we know, really there is this little S symbol, and this lets us know that we're now in S space, much like how you might see something like this, where this denotes that we're in T space. Does that make sense? Okay, cool. So at this point, we want to perform some simplification. So we'll look at this and see, okay, so we have our initial conditions. We can plug them in, and that should simplify this a little bit. So let's see. This s squared y will be the same. And let's look at this next one. So this y at 0, it's just 0, so I can just cross that out. All right, so we go into the next one. So this guy is going to be minus 1. So I can just plug that in. So we're going to have a minus 1 here. Now let's look at this next one. So we're going to have sy. And then like we had before with our initial condition that y at 0, it's just 0. So we're just going to have this guy. So now let's combine what we can and factor out our capital Y. We can simplify this even further by moving that 1 to the other side. Oh, snap, that was a horrible S. All right. Okay, now let's move everything to one side so we have capital Y is equal to whatever else that we have in terms of S. So that'll turn out to be Y is equal to 1 over S squared plus 3S plus 2. All right, let's see here. Let's check my notes. Exactly. And do you know what that is called if when it does that? This is called the characteristic equation. And you're exactly right. That's a really good observation. It will always mimic what the original function looked like. So that's a really good way to what? Well, no, that's a good point because we can stop at this moment and think to ourselves, are we on the right track? Well, if we have the characteristic equation, then we are. It means our algebra was correct. And that's usually what clobbers us at this point in time. So let's see. So now that we're at this point, where do we go from here? If you were to venture a guess, how do we proceed in solving this? What might we be doing? Exactly. We're going to be doing some factoring. Oh, wait, whoops, I should not have done that. We're going to get that back. Okay, so let's look at this and think, how could we factor this? All right, well, we have a 2 here, and then we have this 3 here. So what if we did something like, so we need at least this 2 in order to get this 2 right here. But what is this next one going to be? Oh, let's get rid of that. So we have one section here factored out. What is this exactly? Yeah, it's not too bad. This problem's pretty simple. Okay, so now at this point, what we're going to have to do is we're going to have to do our favorite thing, partial fraction decomposition. Yay! So let's get started with that. So we're going to set, sorry, what was that? So you can try to, so there's a specific reason why we're going to do partial fraction decomposition in this situation. Because if we're able to do that, we should end up with, let's get rid of that. We're going to end up with something like, oh man. Oh man, if I can write, there we go. So we know from our handy dandy handout sheet what these would look like if we were to do the reverse Laplace transform, right? That's easy. The question is, why would we want to do this compared to just doing the reverse Laplace transform now? It's because there's a certain property of the Laplace transform that makes it so you cannot do that. You cannot, the Laplace transform of A and B, let me see. Oh, wait, hold up. Wait, let me see. So, oh yeah, here we go. This is not equal to that. What you instead actually have to do is use the convolution. Have they mentioned that in your class yet? Exactly. That's why we don't want to venture down that route. This is unknown territory. So you can kind of go that way, but they haven't given you the tool set to handle that. Does that make sense? So effectively, if we see on the left side, we have y, capital Y. And what is that? It is the Laplace transform of y. The whole goal is we want to find a function of y. So just y on the left, and then some function of t on the right. Because this would be our solution to our original ODE up here, because this has derivatives in it. So we don't really know what y is. Y is some function of t, but we don't know what that is. So this whole process is a way to use the Laplace transform to take these algebraic structures is what they are. And yes, if you look at Gilbert Strang's videos on YouTube, you know, the author of the book that I think they use, right, in LinDiff still? No? Yes? Yeah, that's how he describes it, is it's a way to solve these things because derivatives times things, that's so much work. That's complicated. We can cheat, well, in a good way, and use the Laplace transform to solve things. Because the whole goal is to find out what y is. Does that make sense? Okay, cool. So let's keep going with our favorite thing, our favorite pastime that we'll spend our spring break on, which is partial fraction decomposition. All right, so let's write this out. And if you want a quick review on partial fraction decomposition, we on the Engineering Math Resource Center website have a very good web page that goes back over in case you have some questions about it and might have forgotten some things. Okay. Yeah, see, even one of the tutors is going there right now. See, it's that good. Okay. Partial fraction decomposition. Yes, okay. So now we're going to work through this. We're going to get this 1 is equal to a times. And does it make sense what we're like, why we're setting it up this way and everything for partial fraction decomposition? Okay. Okay. So in this case, I'm just going to do s is equal to minus 1. And so then we're going to get this 1 equals to b minus 1 plus 2. And then that means we're going to get just 1 equal b, which is really handy. We do not like fractions in partial fraction decomposition. And then next we're going to set s is equal to minus 2. And so when we go through with that, we're going to have 1 is equal to a minus 2 plus 1. And that means that a is going to be equal to minus 1. Oops, yeah. So let's set this back up again. And if you have any questions, feel free to ask me at any time because this is kind of long-winded for the Laplace transform. It should be the Laplace transform. Oh man, I'm really on a roll today, aren't I? Cool. All right. So at this point in time, if we take out our handy dandy reference sheet, do these look like something that we might have seen before? Because right now, our next goal is to do what to these right here? What do we want to do to these guys? There's a very specific operation we want to do. Exactly. The reverse Laplace transform. So what that's going to look like is what if I were to write this out all the way, is it'll look kind of like this. Okay. All right. So this first guy right here, what does he look like if we were to look at our handy dandy sheet? What would that look like? E to the, sorry, what? Yes, but what will that A, well, e to the A, yes, but what will that A be in this case? If we have this S plus 2 e to the minus 2t. Because if we look at it, e to the at, if we do the Laplace transform with that, it becomes 1 over s minus a. But if a is a positive number, that means that our initial a must be negative. So, all right, we're going to have e to the minus 2t. All right, and what about our next one? What might that look like? It's the same thing, but what will be the numbers? Minus t, exactly. And notice with this guy, when we did the reverse Laplace transform to both sides, what does this y become, this capital Y? It becomes little y. So now we have what our original function is. We've solved it. Our y is this minus e to the minus 2t plus e to the minus t. All right. That is in this case, if you remember up here, this is our original ODE right here in red, but you'll notice there's something missing. So what would this be if our original ODE was equal to 0? This would be, yes, that's because we don't have any forcing function on the right side. So this is just the null solution. Does that make sense? Do you have any questions? No, not necessarily. This is a fairly easy example. The reason we picked one that was really easy is to emphasize how the process of using the Laplace transform, because it's got so many steps in it that we might as well pick an easier problem. Does that make sense? Do you have any more questions? All right, cool. Okay, so let's go back over here. Okay, so we go through here and we find that miraculously, somehow, the solution that I found was correct. Whew, that was a close one. I mean, running the review, if I had gotten the answer wrong, that would have been a problem. All right, so there's also a reminder here that on our website, we do have a table of Laplace transforms, I believe. Also some other handy dandy things on there related to ODEs. If you have any questions, you can check that out, or also, better yet, come talk to us at the EMRC. We love talking to students and helping them out. But yeah, yeah, you know where the ETC is? You just keep going way down and it'll be on your right. We do accept walk-in appointments. So yeah, and this handy dandy sheet, super helpful. So, all right, so let's keep going. Now, you were mentioning how the other problem was a little easy. This is where things get a little bit more interesting. Now we have something on the right side. It's not just my favorite number ever. Wait, is it controversial for me to say that zero is a number? No? Okay, well, if they say no, then it's okay then. All right, so with this in mind, let's transfer this guy over to the other side. What? Sorry? All right. So with him, we're going to have y double prime. Can you see that, right? Or is it a little small? All right, I will write it a little bigger. Yeah, okay. So y double prime plus 5y prime plus 6y is equal to da, cosine of 2t. So there's our ODE right there. And to go along with it, like sprinkles and ice cream, we've got y at 0 is equal to 0. That's great. And you know what's even better is that y prime is also equal to 0. So this is going to make things so much easier when we get there. All right, let's just check one last thing. Okay, yes. Okay, so do you want to have a go on your own solving this one? And then I'll slowly start working through it? Or do you just want me to just go through it? Oh, all right. Okay, sounds good. So from the first, we'll copy the same first step we had with the other problem. We'll just apply the Laplace transform operation to everything here. So we're going to have this s squared times capital Y minus s times our initial condition y at 0 minus y prime at 0. And then we're going to have this 5 times s capital Y minus y at 0 plus 6 times y. So that's the left side, but what about the right side? And this is where things get really fun. Well, depending on your definition of fun, we're going to have the Laplace transform of cosine of 2t. And if we check out our handy dandy reference sheet, we're going to notice that this guy is s over s squared plus 2 squared, right? Yes. Yeah. We'll do that. Or I could just simply write that as 4. So that's that beast. It's a horrible combination. So let's work through this and see if we can simplify it a little bit. And we can see right here with our initial conditions, because all of our initial conditions equal 0, that is going to make our life so much easier. I can just zero out a million things. It's fantastic. So what we're going to end up with is we're going to have this s squared y plus 5sy plus 6y is equal to s over s squared plus 4. All right, so now let's factor out our capital Y. So we're going to have s squared plus 5s plus 6 times capital Y. We're going to have that equal to s over s squared plus 4. Okay, now comes the crucial step where we're going to get y, capital Y, by itself. So we're going to divide out this behemoth of a polynomial over here. And just like you mentioned earlier, notice how this guy looks just like our original ODE, since it is the characteristic equation. Yes. So at this point, we know we did the right algebra. Things are algebraing, if that's a word. So we're going to have y is equal to s over s squared plus 4 times this horrible polynomial. So at this point, what is our next step? What do we want to do from here on out to solve this thing? If you were to venture a guess. You're on the right track, and that would work. Yes, you could do that. Instead of multiplying it in, what I would recommend is you would just factor this as it is. But let's go on that journey and see why we might want to do that. So let's keep going with the idea of factoring because we love it so much. So much factoring is going on here. It's awesome. So if we look at this beast over here, this polynomial, we'll notice that we have this 6 here. And we just understand from divine intuition that we could do something like, let's say, I don't know, like s plus 3 times s plus 2. And somehow we just magically know that. I'm just joking. And we can factor it out that way. And here's why we might not want to have multiplied in this guy into this guy. Because if our goal is to do partial fraction decomposition, when we multiply those two together, then we have to factor them out again. Why do that when we could just keep them separate, factor this guy separately, and then perform partial fraction decomposition after the fact? Does that make sense? Okay, cool. Okay, so let's do some partial fraction decomposition at this point. So this is going to be equal to S over, woo-wee, this is a long one, very long. It's going to be over that. So now let's use our useful knowledge of partial fraction decomposition and set this guy equal to, let me see, AS plus B is going to be this S squared plus 4. And then we're going to have C over this S plus 3. And then we're going to have D, which is going to be S plus 2. All right, and let's keep going with this one. So we're going to have S is equal to AS plus B times S plus 3 times S plus 2. And then we're going to add C times AS. Wait, no, hold up. Whoops. S squared plus 4 times S plus 2 plus D times S squared plus 4 times S plus 3. Okay. So that's a monstrosity we have to deal with. So let's see what we can do from here. Let's see. So one strategy is to just multiply through things. Let's see. Yes, that's how we shall proceed. So we're going to have this S is equal to AS squared plus 2 AS. Let me see. So plus BS plus 2B. And that's going to be times S plus 3. And then this is going to be CS squared plus 4C. And that's going to be times S plus 2. And then we're going to have this DS squared plus 4D. Whoops. All right, and we still have one more step before we can start plugging some things in. We're going to multiply through again, unfortunately. And we're going to get this AS cubed plus 3AS squared plus 2AS squared plus 6AS plus BS squared plus 3BS plus 2BS, let me see, and then plus 6B. And then we're going to add the next guy, which is going to be this CS cubed plus 2CS squared plus 4CS plus 8C plus D S cubed plus 3DS squared plus 4DS plus 12D. Woo! It's a long one. Now you're probably wondering, why on earth am I doing this? And this is because we know that a system of equations is oh so nice. And we can make one. So how we can do that is we're going to look at how many of each term there are. So we know we go up to S cubed. So we're going to start from constant. How many constant terms there are. So for example, this guy, we're going to see how many of them are. s squared and s cubed. So let's see what that looks like with this. So we're going to have x cubed up here, s squared up here, s, and then a constant, and I'll just use pound sign for that. Or is that hashtag? Am I like 15 years out of date for that one? So we're going to see how many s cubed terms are there on the left side. Well, there aren't any, so we're going to have 0 equal to this a, which is right here, plus, let's see, we have c plus and d, a, c, d. All right. So now let's look at our s squared. We don't have any on the left side either, so we're going to set this equal to 0. And we're going to see that we have this 3a. We have this plus 2a plus b plus 2c. And let's see, a 3d. And that's that. And then lastly, well, second to lastly, we look at how many s terms we have on the left. We have 1. So we will just put a 1 on that side equal to, let's see, we have 6a plus 3b plus 2b. Let me see, 2b, 3b, 2b. Oh, and yes, 6a. Let me do this. Yes, yes. 4c. Yeah, that's a horrible 4. Okay, and then let's see, we have 4d. Okay, cool. All right, and then lastly, how many constants do we have on the left side? We have none, so that'll also be 0. So now let's go and see. We have 6b plus 8c, and then plus 12b, or d, I mean, 12d. So at this point, you have some options depending on the course that you're in. If your professor allows calculators, you could plug this into your handy dandy calculator and have it do the work for you. Or worse, you do it by hand. Now, the math department loves doing these things by hand, but I don't. So I'm going to refer to my notes on the solutions for this, if that's okay. If you want, I can kind of go through it. Okay, cool. That'll save us. Yeah, just a matrix. Yes, sir. Live photos. Let's see, where is it? Where did I put that? Here it is. Okay, cool. So we're going to find out that eventually, by some stroke of luck, we'll know that A is equal to 1 over 52. Ooh, it's a horrible number. This is why we have the computers do it for us. B is equal to 5 over 26. C is equal to, oh, whoops, that's a 3. That's supposed to be a 3. 3 over 13. And then D is equal to negative 1/4. So we plug this back into what we have earlier. So we're going to have our capital Y is equal to 1 over 52 S over S squared plus 4 plus 5 over 52 times 2 over S squared plus 4. Does it make sense how I got that? Okay, cool. Let me see. So we got 3, and then the next one is 3 over 13 times 1 over S plus 3. And then last but not least, we have this negative 1/4 times 1 over S plus 2. And so from here on out, thankfully, we can start to see that the end is near with this blasted ODE. So we're going to look at our table of Laplace transforms, and we'll know that when I take the reverse Laplace transform, we're going to have 1 over 52 times cosine of 2t from this term right here. And we're going to add 5 over 52. Wait a second, where did that come from? Is that 2 supposed to be there? It is, so isn't that interesting? Oh, I skipped a step a little bit. Does it make sense how, let me highlight this. We have this, let me see, where is it? This b right here. We're going to transform this guy from here to here. Does this linear progression make sense? Because this top bit right here, I can just split them up because they'll have a common denominator. I can just split them apart. So we're going to have this b over s squared plus 4. But when we look at our table of Laplace transforms, we're going to notice that this looks a lot like sine of kt, but it's a little different. So how do we make this little guy look how it should in order to apply this reverse Laplace transform? Well, we can just multiply it by 2 over 2, right? Because that's just multiplying by 1. We can do that as many times as we want. So that's how we get this 5 over 52. And so we're going to have the reverse Laplace transform of that will be sine of 2t. Now let's move on. We're going to have this one, as we reference our sheet, it will be 3 over 13 times minus 3t, e to the minus 3t. And then our next and final will be minus a quarter times e to the minus 2t. And we're going to look over here and see, is this what it should be? Yes. And as a solution, a very, very long solution, we have this guy. Do you have any questions? I know this was a little long. Okay, sounds good. So with that being said, let me see, where's the mouse? Okay, there it is. Let's go back over here. We'll do this. So here's more of this, and here's more of the solution. You can see this is, like you mentioned, we just form a matrix. We punch that into the calculator. We go, yay, and then we move on. Okay. And there's the solution. I got it right. Wow, 2 for 2. Wow, I'm on a roll today. And I need to hurry up. I need to hurry faster. Okay, so here's the first springs example. Okay.
So do you want us to go through the Springs applications, or I'm pretty sure Matt has more than laying out the first time. So
Okay, all right. Here, let me move my stuff out the way for you, Matt. Do you want me to plug it in now?
Do you sign or do you use this?
I've been using this one. I have the box open if you want me to pull it up. Actually, you'll know where they are. So. Oh, and here's this guy.
Yeah. Yes. All right. So we've got a bunch of stuff to go through, and I know we're kind of short on time. So as I go through, you can just kind of tell me how you feel on the material, and if we feel good, then we can move past it, and if not, we can go through it. So I'm just going to kind of take you through everything about linear algebra, right? So we're primarily concerned with solving systems of linear equations, right? And that's kind of what this right here is showing us. This is our superposition. This is just what it means to be linear, right? So it allows us to basically write a system of equations with these kinds of matrices, right? A lot of what we're doing with linear algebra is we're trying to solve systems of complex equations using tools that make them significantly easier, right? So our large part of that is multiplying matrices. So how do you feel about matrix multiplication? Good, okay. There's technically 4 ways you can do it. Most oftentimes you will just use just the standard one. And it's usually, I think this one right here. Yeah, AE plus BG, right? But you could do it any number of ways, and they end up giving you the same thing. So if you feel good about that, then we can move past it into, and this is just kind of what it looks like, right? Calculating every single one using row and column.
So there's just, it's essentially just a system of equations.
Yeah.
And you're just taking those variables and doing it around. And putting this in column instead of a.
Yes, exactly.
And then just using that too.
And we actually have some system of equations problems in there, so we can go over those. These are just some of the kinds of matrices that you'll see. Oh boy, what was that? So the identity matrix, right? This is just our diagonal of ones. This is essentially like multiplying by 1. And the identity is used for solving system of equations, but it's also kind of just pops up everywhere. The inverse matrix, that tells us the matrix that when you multiply it by itself and its inverse, it'll give you the identity, right? So it just undoes what a matrix is, okay? Permutation matrices, it's any matrix that swaps the rows, right? So you know that we're allowed to do row operations. We are allowed to swap the rows. And it looks something like this, right? Because if we multiplied this by another matrix, all it would do is it would multiply each row by 1, but put it in a different spot, right? So it keeps the rows the same and just kind of shifts them around.
We're allowed to shift just to all.
Yes, right. It's
All just like scale.
Yep. Well, not necessarily scalar multiples, yes, but we're allowed to do what are called the 3 row operations, which you can just essentially shift what order they're in, right? Because it's just like, just imagine you have 3 equations stacked on top of each other. If you wrote one equation before it, it's still the same 3 sets of equations, but you're just rearranging, right? So you're allowed to do that. You're allowed to scale them by a constant, and then you're allowed to subtract one from the other, right?
Because doing those things, well, because I just hate keeping about it. Solving the systems without matrices, because you can do that just because it's every thing's just like not to put over variable.
Yeah, it's because the relationship between them is different. So, and we'll go into that in a little bit. The singular matrix has a determinant of 0, and it tells us a couple properties, but that's mostly what it means. Is if they say find the determinant of a singular matrix, you immediately know it's already 0, right? And again, we'll talk a little bit about the determinant. So yeah, the biggest ones that we're going to be looking at are rotation matrices, and they follow this kind of weird format. But essentially what this will do is imagine you have a set of points, right? You can plug in an angle right here, theta, and it will rotate that around the origin, right? And so we can use that for some interesting things. There's a couple applications of that we can touch on. So yeah, those are just kind of the sum. And then the next big one is the elimination matrix. And this is kind of the final really big one. And it just tells you how to do removal of certain things. So E21, for example, shows us how to remove the second row in the first column, right? Because that's how we do like reduced row echelon form, right? You remember that? Have you heard of that? Elimination matrices basically just give us a visualization of that process. Okay, so we're going to do what's called elimination matrices. Have you done a lot of work with them? somewhat? Yeah, more or less. So the question says, given this matrix, find a matrix that will eliminate the entry 3, 1, right? So that's row 3, column 1 right there. And so I've got it kind of set up here. And we want, yep, 3, 1. So we want to eliminate this.
I guess why are you wanting, what's the point of it?
Yeah, that's a great question. So the reason that we want to eliminate certain members of a matrix is because we can set it up in a very specific way that will basically give us the answer to a system of equations. And it's because if we can get it into a form like this, right? Something like upper triangular form equals and then something else, right? Where all we have is ones right here, then that's just giving us the answer to our right? And so by eliminating certain things, we can also find certain characteristics of the matrix. So we'll go over what are called the 4 spaces of a matrix. And you need to remove certain things from it so you can find the right space, right? And the space will then tell you what solutions are viable, what things aren't possible. So it's kind of just a tool that lets us see different parts of the equation. Does that make sense? So what we're going to do here is when finding an elimination matrix, what you do is you always start with the identity matrix, right? That's always just kind of your base point, right? Because we want, ultimately the goal is to find one matrix that can multiply into this one and then just get rid of that 8 force, right? So we'll start here.
Different questions.
Yeah, go for it.
This lecture, like, it's sometimes hard to, like, what we're doing, we're like putting a number of matrices together that would multiply that by, like, it would get rid of that. Because you could just like put in spread echelon form and just like get the answer.
Yes.
Is there, are both of those like fine?
Yeah, so if he
Is there
asks,
benefit to doing this maybe?
one of the benefits of doing it this way is that you can do quite a few complex things and then put them into one single matrix, right? So right now the question is only asking us to do a single thing and it's remove 8. But if, let's say we needed to remove the 2 and the 8 and the 3, and that gets us into somewhat closer of a row echelon form, what we can do is we can find 3 individual matrices and each one will explain one step of the process. Then you can combine them into one big elimination matrix. And then that single matrix will do every operation for you. Does that make sense? So the reason that we kind of care about elimination matrices is because you can do translation and elimination and, and then you can combine it kind of all into one big matrix, and that matrix will take care of the entire process for you. So that's kind of why we care about these little individual ones, right? So the first thing that we do is we say, what kind of operation could get rid of the 8, right? And so I think you can pretty much see it's going to be 4 times this row, and we're going to add it to this, right? Does that make sense?
Yeah.
So I'll write that out. 4 times row 2 plus row 3 equals row 3, right? And that will get rid of the 8. It'll also change up the rest of the matrix, but we don't really care about that right now, right? What we care about is getting rid of the 8. So what we're going to do is we start here and we say, what row do we want to add to the other one? So we know that we're changing row 2 and we're going to use it to manipulate row 3. So that tells us that in our identity matrix, we are going to be changing that color actually. We are going to be using this column, right? So we're changing column 2. And so we're going to then be kind of stationed in column 2. Or sorry, we're changing row 2, so we'll be in column 2. Then we need to change column 3. We need to change column 3. And so we're going to find row 3, right? So what that says is we've got to change this guy right here. Do you see how he's kind of at the intersection of those 2 places? Right, the green part representing the row we're changing, and then the blue part representing the one that we want to eliminate. So what we say then is, what am I trying to read? Our elimination matrix will then be 1, 0, 0, 0, 1, 0, 0, and then this is where we insert our 4 right there. That makes sense, right? At the intersection of the two places that we're most interested in. Okay, so that's just kind of a shortcut into like finding the elimination matrix, right? Start with the identity, find what row you're multiplying, and then find what row you're looking to eliminate from, and it will be that subsequent column and row. Does that make sense?
So you said that there's 4 times the sum. You add it to the.
So now when we take this matrix and we multiply it by our original, right? What this will do is it won't change the first row, right? That'll stay the same because it'll just be 1 times 1 plus 1 times 4 plus, or not plus, but you get what I'm saying? And then the second row will do the same thing, right? It's just a 1 right there in the center. So it'll again be -2, 6, 1. So we know the first and the second row doesn't change at all. But then let's do this third row multiplication, right? So we get 0 times 1 plus 4 times -2, which will get us -8 plus 1 times 8. And then we get -8 plus 8. That gives us a 0. See how that kind of works? So
after that person, you have 4 rows plus row 3 and to do that, and you have that in the third row highlighting. Is there a reason why you have the second column rather than the second in green?
I was just using this as a tool to kind of show you how you can pinpoint which member of the graph you need to insert the 4, right?
Yeah.
So when we're taking, because you could think of it in terms of multiplication, like matrix multiplication, and you could think through and say like, okay, I know that if I change this one, then it will multiply something in the second row, and then this one will, or you could just kind of use this little trick and you could say, okay, I'm multiplying a constant by a row, and then you find that column, and then whatever row you're trying to change will then be that row. And then that just kind of gives you like an intersection, and then that's how you know where to put the constant. Does that make sense? But that's just a product of the way that we multiply the matrices. Cool. Do you feel good on that?
Yeah, it's a column.
Yep, and it's just these colors that I've got here. So if we're trying to multiply a constant by row 2, then we find our second column. And then if we're trying to change row 3, that will be in row 3. So then we know row 3, column 2. And that's the exact point where we put our constant 4. Is that all good? Okay. And this next slide kind of shows you basically the same thing. You start with the identity. You identify which row you want to change. So we want to change row 3. And then we're going to use row 2 to do that. So we identify column 2. That gives us that little intersection point right there, the bottom 0. And that's where we put our 4. Cool. Do you want to do another one or you want to move forward? Yeah, for sure. Yeah, for sure. We can send you a presentation. If you just want to talk to me after, I can get your emails. Cool. Do you want to do another example? Or do you want to move forward?
Sure.
Okay. So same kind of thing. So this one's a little bit longer. So this one we want to put it in upper triangular form, right? So this is one of those examples where we want to do a couple steps using one single matrix. So the kind of idea with this is we're going to find 3 separate matrices that each get rid of one member and multiply them all together to get one single elimination matrix, right? So we're going to start, we want to take away this, this, and this, right? Because that's what upper triangular form is. right? We want these to be zeros. So basically,
Is there a reason why it's not like? Like the top triangle or something?
Um,
All of the triangle?
yeah, the reason that it's because we want the like we want the should I have backwards? No, sorry, you're right. I have a flip, right? So upper right triangular form will be the zeros in the top. Right? So we actually want it.
Also,
Yeah, it is. So it'll look something like 0, 0, 0, and then we'll have numbers like that, right? So that's what we're looking for. Okay, so the first thing that we're going to need to do is we always kind of work in this pattern. We start here in the first column, and we go top to bottom. So we'll start by eliminating 1, and then eliminating this entry, and then we'll go into the second one, and we'll work from there, right?
So you want to off taking the 4 negative 0, or are you separate one with 7 zeros?
We want sorry, let me just yes. Okay, sorry. So it's kind of confusing. The matrix that we get that does the elimination process actually ends up being a lower triangular form. So the elimination matrix that we use to do that will look something like this. But the output that we want is going to be zeros on the bottom. Sorry, does that make sense?
So the upper triangle,
Yes, means
you want,
numbers in our upper right.
so we want, and then we want zeros.
Zeros on the bottom. Sorry about that. Okay, but yes, so the elimination matrix will be a lower triangle. So kind of interesting how it works out that way. Okay, so first thing we want to do, right, is figure out what row operations we need to do. So we need to first eliminate this. So we're going to take 1/2 of row 1, and it's got to be negative, right? And we're going to add that to row 2. So that's kind of our first one, right? So if we do that, the matrix that we get will look something like, that'll give us a matrix that looks like this. 2, 4, 2, 0, 1, 1, 3, 7, and negative 1. Right? So we take half of 2. We add it to the second row, and so we'll get 3 minus 2, and then we'll get 0 minus. Right?
Is that the result? So is there a matrix or
This is, so what we kind of have to do first is we have to identify what steps will get us there, right? Because now that we've, like, this one doesn't highlight it exactly, but when we eliminate the 3, this 7's going to change as well. So we're not exactly sure what we need to eliminate yet, because this 7 could become something else. So what you do is you kind of outline your steps one at a time. And then once you've outlined them, then you can create all of the elimination matrices kind of at the end. Does that make sense? Okay. So that's kind of the first thing we do, right? And then,
so you just change row 2.
yep, we can only change one row at a time, right? So that just gets rid of that 1. Do you see how we have a 0 there now? So now we need to get rid of this 3. So we're going to do something similar. We're going to do the operation R3 minus, I'll do it in the same kind of format. So we'll do negative 3 halves R1.
Now we're basing it off the matrix we just got.
Yes, we're basing it off of this one, right? Because we have to use the matrix that we have. This one is still using row 1, so it's kind of the same either way. And then we'll assign that to row 3. All right, so then our matrix will look something like this. The top won't change. And this should be, and we'll get the same second row, right? And then the third row will change and it will be 0, 1, 2. So that's what you get for doing that. Cool. And then now it's really easy. Now all we have to do is get rid of this 1 right here. See how that 1 is now different than the 7 up here originally? And that's why we have to kind of write out all of our steps beforehand. So now we just need to do negative row 2 plus row 3 and row 3. Right? Because that will then give us 2, 4, negative 2, 0, 1, 1, and 0, 0. So now our matrix is an upper right triangular form, right? And we've kind of outlined the 3 things that need to happen. And we're going to create a matrix for each one of those steps. Does that make sense? Okay. So the elimination matrix number 1, what do we always start with? Our identity. Okay. So now we've laid it out really easy and really simply. So we say we want to change row 2, right? Row 2 is what's being affected. So we're going to have to find something in row 2, or sorry, row 3. No, row 2. Row 2. Right? And we're going to be using row 1 to do that. So we find column 1. Right? So we see that we kind of have this intersection in the middle left-hand side, right? Does that make sense how I found that one right there? Yeah. This one right here. Row 2, column 1, right? So we always look, I'm changing row 2. So I find row 2. I'm going to use row 1 to do that. And so then you find column 1. That's just kind of the pattern, right? And then if you use negative 1/2 row 1, that's where you throw your negative 1/2. Does that make sense? So this matrix E1 now does all of step 1 for us. We're going to do that 2 more times. So I've got E2. We are trying to affect row 3. So I'm going to put our identity in. We're affecting row 3, so we're looking at row 3. We are going to utilize column 1. So we'll be column 1. And so right there at that intersection, we will get negative 3/2. Does that all make sense? Okay. All right, final one. Where luckily this one's pretty easy. Start with our identity. And then we say, all right, changing row 3. So this will be in row 3 again. We're going to use negative 1 R2. So we find column 2. And we throw our coefficient right in there. Okay, so now we have 3 matrices. These matrices will do the steps outlined right here. Okay, how do we combine these 3 steps? We multiply them. We multiply them each together. And a really important part of this is there's a very specific order, right? When you multiply matrices together, yes, A times B is not B times A. They are two different things, right? So the order that I always think of is we start with our matrix and we move left, right? Because we want some output on the right over here. We want upper triangular form, which we know is 2, 4, -2, 0, 1, 1, 0, 0, 1, right? And then this is our original matrix. And we're going to multiply that whole thing by E1 times E2 times E3. Does that make sense? Oh, yeah, sorry. Wait around. Thank you. E1, 3. There you go. All right, so we always work from the equal sign outward to the left. I don't want to take up too much time doing that matrix multiplication.
That's, you want to get some.
Well, it's up to you, right? So this kind of outlines just exactly what we did, right? We first find a way to eliminate them. We outline the 3 steps we got to take. Then we find each of the 3 matrices and we do all 3 of them multiplied together. And then this is what you get. So you'll get one matrix, and this is our lower triangular form elimination matrix. You see that? So this is E1. This is E2. This is E3. Right? Oh yeah, for sure. Yeah, so this is the first thing we did. We outlined the 3 steps. So this is the first step.
Sorry, still just.
Oh, yeah. Right here. Yeah, no problem. And now I'm moving a little quick. Yes, so we have to still multiply it by the matrix. And so this right here is what we call the elimination matrix. And then this is just the original matrix we started with.
You have the elimination matrix for this.
Yeah.
I'm gonna check my answer to that.
I had it pulled up just a second ago. It's on the other slide, but I don't want to move past
Does it
it.
also normalize it? So I mean, first row 1, 2, -1. So 2.
I've got in my notes here, it's 1, 0, 0, -1/2, 1, 0, and -1, -1, 1.
Okay, I got 1/2 0, 0, 0, 3/4.
Okay.
But I think it's just because I applied that in first row line too.
I think so, yeah. If you got these 3 right here, like if you got the same thing here, that's really what's important for this, right?
So you multiply E by that.
Yep, and then it does all 3 of these in a row, and it will give you the matrix, the brain. Does that make sense? Cool.
So that E. Elimination matrix, yeah. That's what we're looking for.
Yep.
Multiply by that. So
This right here is the elimination matrix. All 3 of those things multiplied together. Cool. We good? All right. So that's exactly what we see here, right? Row 2 minus 1/2 row 1, row 3 minus 3/2 row 1, and row 3 minus row 2. And then we get the same upper right side triangular form. And then this just shows us combining E1, E2, and E3 together. Cool. Okay, these are the 4 fundamental spaces. So the column space, the null space, the row space, and the left null space. They're not too hard to find, but they're going to be using the same kind of row operations that we've been talking about. So the column space is just all linear combinations of the columns in your matrix. So you'll get, we'll go through an example. So I'll just kind of describe them here, and then we'll go through an example. Basically, you're going to find all the linearly independent columns, right? Then your null space, this one's important. It tells you, you find the vector x that when you multiply by a will give you only zeros. Right? So you basically find where it's null, zeros. Your row space is the same as your column space, but you do it with the transpose of A. And then the left null space is the same idea. It's A transpose Y equals 0. So there's really kind of two spaces that we think about, and then we transpose them, and that gives you the other two. Right? So we'll go through an example that kind of clarifies what each of these means and how you find them.
To visualize these spaces that are out.
It's a little hard.
That's what I understand what they are, why they're important, like what they look like, kind of.
Yeah. So when we get pivot columns, right, we have what are called free variables. So they're basically variables that can change, right? So we have this system of equations, and our pivot variables are variables that are kind of defined for us. And the free variables can kind of change or interact, or they can scale and stuff like that. And so, yeah, it's kind of tough to visualize, but if we go through the example, maybe, no, right? So the question basically says, find the four fundamental spaces of matrix A. So the first thing that we got to do is we got to put it into reduced row echelon form, right? And so what we're going to do is we're just going to do our row operations. And I'm going to do, we're first going to get rid of this one right here. So we're going to subtract the top row from the bottom. Right? So we'll get 0, 0, 0 minus 1, still 1, and then 6 minus 2 is 4. Right? So this is just row 3 equals row 3 equals row. Okay. Then we notice that these two rows are the same. So we can just do one minus the other, and we'll get a row of zeros. Okay, so now I'm going to outline what I was talking about just a second ago, these pivots. Right, so we call these our pivots. Basically, it is the first non-zero number in every single row. Right, so starting from left to right, you move until you hit a number. And once you hit a number, that's your pip. Does that make sense? Okay, so what that leaves us with is these two things right here called free variables, right? And the reason we have free variables is because these things are right here, they're the same, right? They're a scalar of each other, they're the same thing. And so it kind of leaves us with options, right? So things in the squares are pivots, and then everything else is a free variable, right? So the column space tells us about our pivots. So if we find the column space, there's two pivots, and then there's two free variables.
Can you look at it as variables, is the number of columns or number of pivots?
Absolutely, yeah. So just any column that doesn't have a pivot gives you a free variable. Yeah. So,
like they're not the pivot, the free variables.
no, it's the variable like assigned to it. So in this case, we would say x1 and x3, right? Because we always got to remember that we're doing this in terms of like coefficients of a system of equations, right? So x1 and x3 are pivots, and x2 and x4 are variables that can change, or free variables. Does that make sense?
So there's just pivots because the values are 1.
Yeah, so not necessarily because they're 1. We just always, to find a pivot in a row, you start at the left and you find the first non-zero entry. So as you can see, this is the first non-zero entry in row 1. And then we move, we have 0, 0, and we find a non-zero entry, so it's right here. And then this is all zeros, so we don't have any pivots other than x1 and x3. So
Okay,
that makes
but
sense.
in reduced row echelon form, that pivot will always be 1.
Yes, in reduced row echelon form specifically, it'll be 1. Cool. So to find the column space, it's pretty much as easy as it sounds. You look at the columns associated with your pivot variables. So I'm just trying to find it.
1, 2, 0, 0, 1, 2.
Yep. So really quickly here, the row space, if we go back, right? So the row space is what we, right here. Or actually the column space, we'll get to the column space in just a second. We're going to start with the row space. Because the row space, you can find the non-zero from RREF, right? Because we're allowed to do row operations, we can take the row space of our RREF, a reduced row echelon form. So for the row space, a little transpose there. The space looks something like this: 1, 3, 0, 2, and 0, 1. So right, this is our row space. Right. So
Be okay to write them word for word as well.
yeah, I mean, just like in Strang's textbook, this is usually how he writes it. You usually see them as rows.
I don't know, that's the example. That's how the transport is, like. Well, I guess you didn't.
Yeah. So, and then the column space is kind of interesting. The column space, what's tricky about it is you have to take the columns of your original matrix, right? Because we're changing up the rows and we're allowed to do row operations, we can use the rows from our reduced row echelon. But our columns kind of change differently. We're not doing column multiplication or column algebra, right? So what we do is we say, okay, we have x1 is a pivot and x3 has a pivot. So we go back to our original matrix and we find the columns there, right? So the span will look something like 1, 0, 1 and 0, 1. Right? Does that make sense? We can't take these rows or these columns. Cool.
Sorry, you said space. So it's the column space of the transpose, right?
Yeah.
So.
That's where you get this kind of notation C, a transpose.
What's the transpose? Are we looking at the transpose of the original or the transpose of the reduced version?
The transpose of the original. Let's see, this is our A matrix right here.
Yeah.
So if we look 1, 3, 0, 2, that's like if we transpose that, that would be our first column, right?
Yeah.
And if we transposed A, this would be our second column.
That ain't just the first two columns.
Well, it's because right here, you don't actually need to think of it like in terms of really taking the column space of the transpose. You can just look at the rows. I mean, you could. The easiest way is to identify is the rows in the reduced echelon form.
So all the rows we have, those columns.
Yes. So the only one that you like in order to find the space really need to transpose is for the left null space. That one you like do have to find the transpose and reduce echelon form that one. Right. But otherwise, we just find the rows right here.
So why do we take the vectors for the row space from the reduced echelon form, but column space from the original matrix?
Yeah. So the reason that we do that is because we're allowed to manipulate the rows in the matrix, right? So I can say row 3 equals row 3 minus row 1, right? And they still stay in like the same relationships. So we've identified that row 2 and row 3 are identical, right? And so that is something that we can, that like, or they're scalar combinations of each other, right? And that's still true right here in the original matrix, right? So as we move and manipulate these rows, their relationships still kind of are the same, right? So we can take the row space because we're using rows that share the same relationships from when they start to when we get reduced real echelon form.
Okay, so basically, if I understand this correctly, we can do that because they're still linear combinations of one another.
Yeah.
And we just take the simplest version that we can, which is from the reduced echelon form or from the column space. If we change them, they're no longer the same relations to each
Yeah,
other.
they're not related to each other in reduced real echelon form the same way they are in the very original matrix.
Okay, so we just have to take.
So we have to go back to the original matrix.
Okay.
Does that make sense? Okay, the null space of A is where we solve for when our REF equals 0. So we're solving AX equals 0. And the easiest way to do that is reduced rest-flow form, right? Because we're taking basically a system of 3 equations, right? And we're solving when it equals to 0. So if we use in terms of our x variables here, this is like saying x1 plus 3x2 plus 2x4 equals 0, right? Because we're setting this matrix equal to 0, and we're just outlining 1, 3, and 2. Does that make sense where that came from? And then our second row right here tells us that 3x3 plus 1x3 plus 4x4 equals 0, right? Yeah.
So for our null space, why don't we just choose a vector of zeros, or like the 0 vector at a time?
So that like technically is, but it's called a trivial solution, right? And basically it just tells us that like, yes, that's correct. It is a null space, but
Wow, 0 is 0.
exactly. It doesn't give us any useful information. So yes, that is always kind of an implicit trivial solution to it, but we are more interested in what constants we can assign that are actual values that give us zeros. Right? So what you can do here is I'm going to say x3 equals negative 4x4, right? Just kind of rearrange this. I'm going to solve x1 equals negative 3x2 minus 2x4, right? So we know that there's going to be a dimension of 2 because the dimension of our null space is always going to be equal to the amount of columns minus the rank of our matrix, right? And the rank is just the number of pivots, right? See, if you ever hear a rank 2 matrix, that just means there's 2 pivots in the matrix. Okay? So we know that it's going to be a span of 2 different vectors. That's the same as our dimension, right? And we've got to find 2 vectors that make this system of equations 0, right? So one of the easiest things that you could do starting out is plug in a couple zeros, right? We don't want everything to be 0, but most oftentimes your null space will involve zeros. So I'm going to start by saying x3 and x4 are 0 and just see what happens, right? So if I set those equal to 0, yeah, go ahead, of course.
So it's just find the null space, so just how this use the formula of negative I.
Mhm. Yeah.
Being like, I get them
Yeah, so you can find the null space in different ways, right? As long as what you end up with is a span where you could linearly combine any scale of those 2 matrices, right? Or any scalar of those matrices or vectors and still get zeros, right? So how you get there, if your professor teaches you another way, that's great. I know some students who can also just kind of like look at it and they're like, well, if I do 0, 0, and then this here, then they can kind of identify it. But one of the ways you can do it is just by solving the system of equations, right? So if I say x3 and x4 equal to 0, right? That's 0 equals 0. That satisfies, right? And then we have this part right here will go to 0, x4. So all we're left with is x1 equals negative 3x2. So if I just say x2 equals 1, then I can solve for x1, right? And that'll give me negative 3, right? So this is like kind of like a little bit of a trial and error approach, right? We can just assume, you know, if we plug these into zeros and the rest of it doesn't solve the zeros, then it's a non-trivial solution, right? And then sometimes you'll end up with scaled answers, and then you just want to scale them down. So if I ended up with like 2, 2 right here, I could scale that down and it would be 1. But this is about as far as we can scale that down. So that's one of the two. Okay, then another kind of easy solution is just try ones, right? So if I said x4 equals 1, then I can solve for x3, right? x3's got to be -4. Okay, so then if I plug in 1 here, I get -2. And I can do the same kind of thing where I say, okay, I know I have to solve x1 and x2. What if I just assume one of them can be 0? And let's see what happens, right? So I have -4, or sorry, -2. This is going to be 0. So I have x1 equals -2. So then you can try that. That makes sense? So, and again, if you ever do this process and you get like a scalar, like 2, 2, 0, 0, you can scale that down. So it's 1, 1, right? Because what we care about is the scaled combinations of these measures. Right? So, yeah, of course.
It's not known, just the one we just had. The one, the first two is, and then it's just like 2x2 identity, 2x2 F matrix, but this one is a little weird because it wants to offset.
Yeah.
Right? Can you show me what, like, I would be.
Yeah, so I actually, my professor didn't go over that a ton. So I think I know what method you're talking about, but is that where you like have the identity kind of square in the top left? And you've got,
Yeah, so. It's just.
yeah, actually, let me see. I don't think, when I took linear algebra, I didn't actually take them.
What the negative at for that?
Yeah. So like, if it was, if you had reduced the rush, yeah, like. This one. Well. Just tells us like the force state, so I think it's confirmed too. So. I also, the class average was 67, and I got an 80, so I'm also.
Yeah, I think that's, I've seen this kind of pattern before. I took linear algebra and I did
Oh, yeah, you're good.
and so I actually didn't take them, but you yeah, I didn't think you could have them, so probably that's.
Okay, yeah.
But I've seen that from other students, I've seen like people in Lat Center,
Yeah.
and Lat too, so.
Cool. So,
On the city.
You'll find that with a lot of linear algebra, there's a lot of approaches to take a lot.
yeah.
Like I said, some people just kind of guess and check, like they just look and they're like, well, if I try this, does it work? And then they go, nope.
I love how real mathematicians just get in check.
Did you know that? Would you have it?
Yeah, I wasn't sure.
I don't know, because what I was thinking is you'd do like a column swap, but I don't. Column swap.
Yeah.
Hypothetically, that way it'd be like -3, 0, 1, 0, and then -4. But I don't know if that column swap operation is entirely allowed or not.
Yeah.
I'm the best guy wins tomorrow. Yeah, just getting off on best. Surely no. I think that's what you do though, because your other two columns are columns for the sit level. Yeah.
And then your left null space is the same as your null space, but you take the reduced echelon form of your transpose matrix, right? So it's the same kind of process. It's just transpose and find null space. Cool. All right. Sorry that was kind of rushed. Hopefully it was somewhat helpful.
You're gonna go take it right now?
You got this.
I got that later. And we just covered everything in this one.
I need to do anything to save that video.
No, you just end it. You should save it.
Just right there.
Are you cool if I give you my email?
Yeah, for sure.
Recording it, those slides.
I think Connor, you'll have the recording. Does it send it to you, or where does it end up?
Okay, I don't know. Let's see what happens. Let's try to stop this and see.